There are many complex environmental parameters that drive corrosion, and the interaction of those complex parameters often affect materials in ways that you would not expect.
You may look at a piece of equipment and on the outside it doesn't look like it's got that much rust on it or that much corrosion, whatever on there, but you'll find out as soon as you get in and turn it on or you try to use it, it does have corrosion.
So corrosion can take many forms, and it can impact the Army in many ways which we truly are not fully cognizant of.
Waiting for things to rust and corrode and monitoring the natural environment can give useful data, but this isn't always efficient. Sometimes we need to speed up the process to get the results we need now. We simply can't afford to wait for weeks, months, or years of testing and data to obtain results. Corrosion testing has proven invaluable, but what about accelerated testing? What if the aspects of the environmental conditions like temperature, sunlight, salt deposits, acidity, and rain that are known to accelerate corrosion are manipulated? Then what kind of results would we get? Hi, I'm LeVar Burton. Join me as we discover some of the most interesting and challenging corrosion test sites in the world. From the relentless humidity in the tropics of Panama to the Arctic climates of Alaska to one of the hottest and driest deserts in Arizona, we will learn why these harsh environments are so unique and so important to our future. Let's start with the problem. Corrosion has been termed the silent and pervasive menace. Now, nowhere is this more noticeable than for the metals commonly used in military and civilian infrastructure and systems. Corrosion testing is critical because it could potentially save billions in unnecessary costs, and more importantly, can save lives. Our military readiness and safety is paramount to our future, and having tools that function properly is critical to our success. There are 4 classes of corrosion tests: benchtop, accelerated tests, natural exposure tests, and in-service or field tests. Now, with each of these tests, there are advantages and risks. Benchtop testing is generally conducted in a lab under carefully controlled and reproducible conditions. These tests are relatively quick and inexpensive and are usually done on relatively simple specimens such as coupons. While these tests are useful for studying corrosion mechanisms, they generally do not translate directly to operational systems. Accelerated corrosion tests are performed in test chambers that can simulate a wide variety of corrosive environments in a controlled fashion. Variables such as humidity, temperature, UV light, and even exposure to corrosive gases are manipulated to induce high rates of corrosion on test specimens ranging from coupons to assemblies such as starter motors. These tests are relatively quick and inexpensive, but the simulated corrosion environment can produce results that are markedly different from those seen in service. Natural exposure tests are done under natural conditions and not tightly controlled. They're typically performed in harsh environments to produce results more quickly than would be seen in service. These test sites vary over time and have different corrosion severities. Specimens can range from simple coupons to mock-ups to full-scale components. The results have relatively high reliability and can translate directly to in-service applications. Compared with benchtop and accelerated testing, natural exposure tests are expensive and may take longer time to produce results. In-service or field testing involves monitoring the performance of materials on actual systems in their operating environment. These tests more accurately represent operational conditions, but can have drawbacks. They may take years to conduct, and because the environment is not controlled, it's hard to make broad conclusions. Also, any full-scale tests may be prohibitively expensive. The bottom line is that all methods are useful. However, corrosion tests that accurately resemble the intended system or equipment operation environment and exposure duration provide the most accurate and reliable results. But we can't afford to wait for the perfect test conditions, so we've got to turn up the volume a little bit to get the results we need. Now, how do we do that? Let's begin with where I am now. I'm just outside of Carson City, Nevada, in the foothills of the Sierra Nevada Range. This semi-desert climate is the site of a very unique vehicle testing facility. U.S. military vehicles are some of the most rugged trucks in the world. They can traverse a variety of terrains that would make a normal truck cringe with fear. At test facilities like the Nevada Automotive Test Center, military trucks are put through their paces. There are literally hundreds of different courses and events used to batter and bruise military vehicles, but perhaps none is more brutal than the Corrosion Durability Road Test. The vehicle frame is twisted, the body is pummeled with rocks, and the undercarriage is bashed with boulders in an attempt to break its very backbone. These trucks are built military tough and rugged. However, until recently, military tough didn't mean it was impervious to corrosion. Sure, these vehicles could climb the steepest mountain, repel enemy gunfire, or carry troops ashore in the roughest seas. But compared to your sedan or minivan, it was an absolute wimp. But thanks to the Office of Naval Research and the work of dedicated corrosion professionals, these vehicles now surpass their commercial brethren. Part of the process to demonstrate and verify the toughness of these vehicles now includes corrosion testing of full vehicles where the durability and driving courses are combined with corrosion events replicating up to 20 years of operations in less than 1 year of testing. Now, to the pit. Okay, now, here's the fun part. These guys actually drive these vehicles through a shallow saltwater pit and then through a slurry of dirt, grit, and saltwater, which causes both corrosion and wear inside the joints and crevices, accelerating the degradation of these areas. These corrosive solutions are representative of the typical environments that these vehicles are exposed to on a regular basis. But all of this still isn't enough to accelerate corrosion of these vehicles. What we need is humidity and lots of it. This is a high-temperature, wet, nasty environment, which is the workhorse of the vehicle corrosion test, the humidity chamber. A vehicle will soak in this environment for up to 8 hours a day at 140 degrees Fahrenheit and 100% humidity, which lets the corrosion process continue for longer than it would under normal conditions. These military vehicles undergo this daily barrage of testing 176 days straight to demonstrate that they can survive for 20 years in the military. And once the driving is over, that's when the torture really begins. Engineers aren't just interested in the corrosion that they can see. They're actually more excited by the corrosion that's not visible to the naked eye. Having a fully capable vehicle shop is a necessity for vehicle corrosion testing. But this shop is currently restricted, so this is the stuff we can't show you. So, here it is, a casualty of corrosion. What was once a capable Humvee is now a rusty pile of scrap that is beyond salvage. There is no way of resurrecting this old devil dog, but like other Marines, this one too has made the ultimate sacrifice. It's given all that it can so that its brothers can live to fight another day.
Vehicle testing, and particularly corrosion durability road testing, is very important during the acquisition process for tactical vehicles to understand materials degradation and the impacts of corrosion on tactical vehicles that you would not normally learn during the standard performance durability process. Corrosion durability road tests have been performed on multiple platforms, particularly done by the United States Marine Corps, and significant findings have resulted from all of those testing programs that have allowed us to find material solutions to corrosion control issues that would be persistent during the vehicle life cycle that we were able to identify and fix during the acquisition process. What's next is to engage more platforms to get them to utilize this protocol, because we understand there is significant benefit from the results that are seen, and we're able to use those results in order to provide more savings to the programs in their total life cycle.
There are several exotic and remote natural exposure testing locations around the world. We have to consider all of the varied climates and regions and be prepared for anything.
Central America, 202,000 square miles of biodiversity with tremendous mountain ranges and fertile valleys, where the trade winds, heavy triple canopy jungle, and high rainfall assist in creating a tropical environment. The tropics are very important to consider when assessing the environmental degradations of systems and infrastructure. This is due to the following staggering statistics. 39% of the Earth's surface is a humid tropical region. They have an average of 400 inches of rain per year. The tropics have had 75% of the world's conflicts since 1960. And the Central Americas are projected to have 63% of the world's population by 2060. These are statistics which simply cannot be ignored. Today, we are visiting this location because major military forces are constantly deploying to diverse environments around the world. Our military forces certainly understand the need for materials testing in these corrosive environments. So it becomes vitally important to pay the cost of corrosion testing now, not only for our national security, but to prevent the even higher cost of lives and systems on the active air, land, or sea battlefield down the road.
If you go to Georgia, you go to Florida, you go to Alabama, wherever you want to go, it's nothing like the real tropics is. I've been in Vietnam myself. I've been on the receiving end of this equipment that's been shipped there. The smallest thing you could even begin to think about may work, it may not work. You may look at a piece of equipment and on the outside it doesn't look like it's got that much rust on it or that much corrosion, whatever on there. But you'll find out as soon as you get in and turn it on or you try to use it, it does have corrosion. It does have the smallest thing in there that you can't operate. It brings the entire vehicle down or the entire piece of equipment down to a level where it has to be maintained.
The facilities we're looking at have been in operation since the 1960s, but jungle exposures can be a serious challenge. The threats are plentiful, and they include not only salt spray, mildew, fungus, UV exposure, dense vegetation and decaying biomass constantly emitting complex fumes. The threats go on to include the 26 venomous snakes, cutter ants, deadly frogs, yellow fever, malaria, dengue, cholera, harmful vegetation, and, well, that's only the beginning of the many numerous hazards to not only systems, but the people using them. There have been some significant findings here regarding environmental degradation. First of all, there is the heat and humidity, which can and do wreak havoc on the various systems and infrastructure. Though the weapons, support systems, ammunition, vehicles, sensor and communication systems are built to withstand the impact of the environment, there are always lessons learned which can be applied. At this point in time, our military is making great strides here in Central America, South America, and indeed around the world. However, the most important thing our military and private industry can do is continue sharing information with one another and make recommendations for corrosion mitigation and sustainment.
There are many complex environmental parameters that drive corrosion, and the interaction of those complex parameters often affect materials in ways that you would not expect and in ways that you could not capture in accelerated laboratory corrosion testing. So let's look at a few of these things and see what really happens with multiple materials. First, in an environment that's extremely corrosive because it's near the coast, you have high chlorides. So you begin to see metals failure. If you look at this, if you look up here, some of those metal pieces are completely corroded in two. You'll also see that you have galvanized materials that have survived better, while you have coatings failures that are extreme. Now, why would that be? Well, one of the things that happens in this environment is you have extremely high ultraviolet. And that high ultraviolet not only attacks plastics and composites, but it also attacks coatings. So coatings failures occur sooner than you would expect in some other environments, but that as a result of the coatings failures, you begin to get failures of certain metallic materials. However, had the galvanized never been coated, you would probably find that it performed fine in this environment. But we are not only interested in metals, we're also interested in concrete materials. So behind me we have here concrete rebar that has corroded, and as a result of that corrosion, it's spalted off the concrete. but you also get concrete failures that are occurring not just because of the corroding rebar. So you have, again, the effects of many factors that are driving corrosion in this environment, and none of those factors would ever be totally incorporated in, or their interactions be totally incorporated into accelerated laboratory corrosion testing.
Different materials degrade in response to exposure to different environmental stressors. For instance, most metals corrode when exposed to salt and moisture, while most plastics do not. Conversely, plastics and composites degrade when exposed to UV light from the sun's rays, while metals do not. Wood degrades rapidly when exposed to moisture, but salt can actually preserve wood. As a result, we must be prepared for all environments and climates around the world. Which brings us to our next location, a remote post in Alaska that was established in 1942 called Fort Greely. Originally, the post was used to teach living and movement under extreme Arctic and subarctic conditions to personnel from all branches of the armed services. Now, this isolated city also helps us understand corrosion and environmental impacts in an Arctic climate. The remote interior of Alaska and the conditions at Fort Greely and Delta Junction can be very harsh and unforgiving, but it also provides spectacular views with snow-capped mountains, local wildlife such as the occasional moose or fox, and the ethereal northern lights dancing across the night sky. Every climate must be explored, from the frigid temperatures in Alaska to beautiful sunny skies and beaches. Let's go now to the tranquil shores of Key West, Florida, the southernmost point of the mainland United States. Key West is literally sticking out between the Atlantic Ocean and the Gulf of Mexico, which provides a natural opportunity for aggressive corrosion. This atmospheric test site has accelerated test chambers, lab electrochemical testing, and pipe loops, but what is the most unique is the immersion testing. They are able to physically submerge a specimen in shallow tanks beachside and then observe up close the results.
So the Navy uses accelerated corrosion testing to support its acquisition planning and design purposes. So for instance, if we're interested in a new material and its crevice corrosion behavior, we might run an accelerated crevice corrosion test to give us a relatively short-term understanding of localized corrosion behavior. Another type of accelerated test we might use is for cathodic protection and understanding how coatings and materials will respond to cathodic protection for corrosion protection. And we'll run a cathodic disbondment test, which is a 90-day test in seawater.
The approach that we're looking at here is the application of real seawater spray onto actual test samples to determine if and to what degree we may get further acceleration of our corrosion rates. Now, what we're using in these tests is several examples of our corrosion test sensors as well as aluminum panels. The same types of coatings evaluated in the same way. We have a spray nozzle which is adjustable in terms of the amount of spray and the duration and how frequently the spray is applied here, and it's as simple as that. So again, it's an open question just what we will get out of this particular technique.
And now, from being underwater to one of the driest deserts on Earth, let's go to one of our most important and extensive test sites located in Yuma, Arizona. Yuma is a subtropical desert climate with extremely hot summers and warm winters. This area is extremely unique. Yuma is considered the hottest city in the United States with a record average of 118 days per year where the temperature reaches or exceeds 100 degrees Fahrenheit. It is also the sunniest place on Earth according to Guinness World Records. The arid desert, the 350 sunny days, and the mere 3 inches of rain per year make this the perfect climate for testing. In 1995, the temperature reached a whopping 124 degrees, so while we all look for shade, let's take a peek at this incredible facility. U.S. Army, Yuma Proving Grounds. The history dates back to the 19th century. It covers almost 3,400 square kilometers and spreads over 2 counties, both Yuma and La Paz. It's located on the southern side of Arizona and represents one of the largest military bases in the world.
The corrosion that you would find in this piece of equipment depends on the environment that it's located. For instance, here we are in the desert, so you're going to have a lot of surface corrosion, which essentially forms a protective film on a lot of the metals and material that you'll find corrosion on. In the tropics, you're going to find a different effect, because as the metal corrodes, it actually goes deeper into that metal part and the alloy, and will continue to break the material down and make it essentially unusable. Now, the consequences to the Army in terms of corrosion, what the effects are multifold, because it depends on what is actually corroding at the time. If it's just a door frame or a metal, large metal piece, protective piece, you can replace that fairly readily or repaint it. But if it's a more critical item, say like a computer system or a data system that needs to transmit, or electronics or things of that sort, communication gear, you're essentially taking a weapon system and making it completely unusable in the field. So corrosion can take many, many forms, and it can impact the Army in many ways, which we truly are not fully cognizant of.
Yuma and these incredibly hot conditions, combined with acceleration tests, have afforded us great knowledge, but it's only the beginning. We are very thankful to the many accelerated testing sites around the world, in association with Aberdeen Proving Grounds in Maryland, the U.S. Army's oldest active proving ground. As you can see, we go through a lot to get results. Every climate has its unique challenges, and materials degrade differently in response to exposure to these climates. But it is our job to make sure we are as prepared and as knowledgeable as possible. The problem is, as scientists and researchers know, with each answer comes more questions. The interaction between materials and the environments in which they are used is very complex. Natural environment exposure testing is the most reliable way of helping to understand this interaction and to predict the performance of materials in the things we use every day. Engineers and scientists are working hard to improve the accuracy and cost effectiveness of these test methods. Prevention and mitigation is critical to the management of corrosion. This is where the efforts of the Department of Defense, in partnership with universities and industry, using elements of science, technology, communication, and education, are truly paying off. The bottom line is, improved corrosion prevention and control practices could help avoid billions in unnecessary costs and help to save lives. So, including accelerated testing expertise and development and the adoption of these test methodologies is highly encouraged. I'm LeVar Burton. Thanks for joining me on this journey through some of the most unique natural environment corrosion test sites in the world. And, as always, remember, rust never sleeps.